Have you ever noticed your ears pop while taking off in an airplane or while climbing a mountain? That little pop is a sign that the air pressure around you is changing. Let's explore what causes this fascinating phenomenon. Atmospheric pressure is the force exerted by the weight of air above us. Imagine a giant invisible column of air stretching from your head all the way into space. That air has weight, and it presses down on you. We define atmospheric pressure as force divided by area, or in formula form, P equals F divided by A. Now at sea level, where that air column is tallest, the pressure is highest. This standard pressure is known to be 76 centimeters of mercury, or 1 atmosphere, which is the same as Psalm 1013-5 pascals. But as we go higher up, like climbing a hill or flying in a plane, the air column above you becomes shorter, meaning less air and less weight above you. So naturally, the pressure decreases. We'll dive deeper into this variation, but first, let's understand why this pressure drop happens. So, why exactly does atmospheric pressure fall as we go higher? Let's begin with air density. Near the surface of the Earth, gravity pulls the air particles tightly together. The air is dense. But at higher altitudes, gravity's grip weakens and air molecules spread out. That's why mountain tops have thinner air. This means there's less mass and therefore less weight in the air above you as you climb higher. And with less air pressing down from above, the pressure naturally decreases. It connects beautifully with Boyle's law, which says that pressure is inversely proportional to volume when temperature stays constant. So, as the volume of air increases due to expansion, the pressure decreases. It's this concept that pilots, mountaineers, and meteorologists rely on to understand changes in altitude and weather. And as you'll soon see in our graph, pressure doesn't just decrease, it does so at a non-uniform rate. Now, let's look at some fascinating experiments and real-life observations that prove this pressure variation. Let's go back to history. Evangelista Torricelli in the 1600s filled a glass tube with mercury, inverted it into a dish, and found that the mercury level stood at 76 centimeters. This was due to the weight of the atmosphere pushing on the mercury in the dish. His experiment gave us the first barometer. Today, we use more modern versions like aneroid barometers in aircraft and even in smartphones. As these devices rise in altitude, they show a steady drop in pressure, a perfect confirmation. Here's a cool real-life impact. Water boils at lower temperatures at higher altitudes. At sea level, it's 100 degrees Celsius. But go to a high hill station and it might boil at just 90 or 92 degrees. Why? Because lower pressure means less energy is needed for molecules to escape as gas. Even airplanes are designed with pressure sensors and controlled cabins to keep passengers comfortable at 35,000 feet. Alright, time to get a little mathematical, but don't worry, it's simpler than it looks. There's a formula that helps us calculate how pressure drops with height. It's written as P equals P naught times e to the power of negative h divided by h. Let me break that down. P naught is the pressure at sea level. H is the height or altitude. H is called the scale height, usually around 7.6 kilometers. This exponential relation tells us that pressure drops rapidly at first and then more slowly as we go higher. This is extremely useful for designing altimeters in aircraft, spacecraft, and weather balloons. Without it, pilots wouldn't know how high they are flying. Now, let's step into the real world and see how this pressure change affects our lives. At high altitudes, the air is thinner, which means less oxygen. That's why mountaineers sometimes suffer from altitude sickness and need oxygen cylinders. Airplane cabins are pressurized to simulate sea level conditions, That's why you feel okay flying at high altitudes. Without pressurization, you'd experience headaches or even unconsciousness. Here's something fun. Try drinking through a straw on a mountain and you'll notice it's harder. That's because the external air pressure helping push the liquid up is lower. And in weather science, pressure drops signal upcoming storms. Low pressure zones often lead to rainfall and clouds, while high pressure brings clear skies. Let's apply all of this with a numerical example. Say the atmospheric pressure at sea level is 101325 pascals. We want to calculate the pressure at an altitude of 5.5 kilometers. We'll use the formula P equals P naught times e to the power of negative h divided by h, substituting values. P naught is 101325, h is 5500 meters, h is 7600 meters. So we calculate the exponent. 5500 divided by 7600 is approximately 0.7237. Now, e raised to the power of negative 0.7237 gives us around 0.4852. Multiplying 101325 by 0.4852, we get the pressure as approximately 49,163 pascals. That means, at 5.5 kilometers up, the pressure is less than half of what it is at sea level. Amazing, right? Let's quickly revise what we've learned about atmospheric pressure and how it varies with altitude. Atmospheric pressure is the weight of air above us, and it decreases as we go higher because there's simply less air pressing down. This concept is backed by barometer experiments, real-world effects like boiling points, and a mathematical model that follows an exponential decay. It affects breathing, cooking, flying, and even weather. Whether you're hiking, flying, or forecasting rain, understanding pressure helps explain what's happening around you. I hope now you understand why packets puff up during flights or why mountaineers carry oxygen tanks. It's not magic, it's physics in action. See you in the next session with another exciting concept. Until then, stay curious and keep exploring.